Good day, folks. I'd like to talk to you today about a device, a better transformer, essentially. I was thinking a lot lately about the backwards transformer configurations and what Don Smith was up to, and even reviewing some old videos, and then something occurred to me, and then I realized, maybe because it was a long time ago when I first listened to the Don Smith stuff, maybe like 10 years ago, and I didn't know as much as I knew today. I did replicate some of the stuff, by the way. It's like one of my earlier videos from a long time ago, so if you want to go way back to some of my first videos called the Kappa Gen, I made a very complex setup without really knowing what I was doing, just from, visual at that point replication. And it actually worked with 2 ground points, and I was sustaining the high kilovolt side with the ground loop and all that. But it doesn't need to be that complicated. And then I later on was able to understand how it really worked and started sharing the concepts and the ion valves and the one-wire diode AV plug systems and all the various possibilities. So I sort of kind of did it in reverse. You see, I built the device first, and then I didn't understand a thing about it. Then I started researching and then figuring out piece by piece how it worked, and then figuring out my own enhancements and then my own conclusions that certain things that Don Smith was doing was either flat out deceptive or not needed at all for the effect. So let me explain here. So I'm actually going to try and draw this here. So we're essentially going to try to build a transformer essentially in reverse. So the idea I had here is, let's have a high voltage source right here. So I'm going to draw my high voltage source, which is, let's say, a neon box. A neon transformer usually is a good prototype for this, but it can be a Tesla coil setup, anything you want, which you feel would get you there. So let's say, we'll say this is 3 kilovolts, high frequency. So I'm just making this up here. Let's say it's 400 hertz, and it delivers about 25 mA. So now we're going to send, now our high voltage outputs are these 2 lines here. That's the high voltage outputs. So let's say, this is pulse, by the way, but we can give it a polarity anyways because it's pulse. So plus and minus pulse. Essentially, you'd want to connect this to, which would be normally a secondary of a special transformer. So on this side here, you're going to want to have a very high impedance value. So a lot of windings, many windings on this one. But it will have to be carefully calculated if you're serious about this. I'm just giving you the working prototype, and I'll explain more about the calculation here. The ratio really matters. Here's our pins here, and I'll draw the core. Maybe if I can find another color here, maybe black, to draw my core right over here. So this is our beautiful core stuff right here. So here's what we would consider the secondary winding. I haven't gone into the primary yet. So what we want to do essentially is connect this here. And over here, what we're going to do is really weird, because I was actually listening to Don Smith, okay? And it was weird because he was doing a demonstration and people were all there taking hard notes like this was the gospel. And I'm thinking, why is no one telling him that he might be wrong in his explanation? So let me explain that. He was saying that he adds on the output side here a power correction capacitor, and that the power correction capacitor must slow down the high frequency. That to me doesn't make any sense, because if you put a capacitor on the output of essentially the AC or pulse side, what you end up having is basically a reactive capacitance. You end up introducing reactive ohms. If anything, that will usually limit what you can use in real power, but not actually shift the AC frequency up or down. That's quite one of the good features of that. This is what I use usually to bring down the AC current without stressing the power supply. Very good trick. But in his application, he was telling people that you must use that, and power factor correction is to slow down the wave. And I'm going, no, it's not. But I think what he was saying, again, because he's deceptive, you need some sort of filtering here. So a basic bandpass filter is essentially something like this. I'm just going to draw it in a square here, where you essentially have, this is very crude here, but you've got 2 coils here, tuned essentially to notch off, with the capacitor here in the middle. And it's essentially something like this, very crude, but there's multiple bandpass filtering designs, and essentially that goes back in here. So this is, I see it's very smooth, so let's just call this bandpass right here. My apologies for the bad drawing here. So essentially one crude form, okay, of filtering. All has to be calculated what the frequency is. So essentially what happens here is you're loading the secondary with what appears now as, because you've got filtering, what it gives you is basically a semi-quasi DC-like bias on the secondary. So you end up having a signal that kind of looks like this with little minor ripples, but mostly a baseline DC. Now for analog circuits and basic loads, this ripple is, you could basically ignore it. It doesn't really matter. So what happens here is we are loading the secondary side with basically very high voltage little current. The higher voltage the better, and I'll get into that. So now here, see, remember, we're building it backwards, so that's why I had to start at what we would consider the secondary here. So what you do here is set up which to me seems the easiest, but there's probably other ways to do it, a second core right near here. And this becomes essentially a low winding, low impedance, 60 hertz primary. So let's say your inverter, let's say it's 100 watts. There's the inverter, 60 hertz, and let's say 100 watts. Not very much, but something's going to happen here in a moment. We're going to send this, we want to modify this essentially. So inverters are pretty easy to modify, but most of them you might not even have to, because most of them are actually pulse DC. You want to send the trigger pulse DC. So usually they're square wave oscillators. Some you have to usually pay more if you want them to be modified sine wave, but that's something you have to really look into. So the output here is pulsed 60 hertz square waves at 100 volts, 110 volts actually. Typical inverter. Now what's going to happen here is the inverter is actually going to, because it's pulse DC, we're going to modulate. So what's that going to happen is it's going to trigger a displacement current because it's modulating the DC, so that's going to move it around. So the higher the potential, the greater the displacement current you get generated here. Okay. That's part one. Now, what we want to do is have a second core here disconnected with a gap here so it doesn't interfere with the primary trigger. And this is basically a kind of a dual primary setup, but we're running it backwards. So same thing here, low windings on this side. Now what has to be really important is you have to make your calculations as if, let's say this is 3000 volts. You want to make it as if the ratio, this would be 110 and 3000 would come out of here, where if you would have, you know what I'm saying? So that's why you're running, this part has to be kind of like a traditional transformer, and you have to be mindful because when you want to step this back down to use it again to real AC, it needs to be, well, it's a lot easier if you make your own transformers and take advantage of the windings to get exactly that 110 here, which becomes an output. And I'll explain that. So what you end up having here, this becomes your output. So over here, we end up our AC 110 volts out. Now what's interesting is on the output here, because it's true transformer, you actually, the square wave ends up being a sine wave at AC, or almost a perfect sine wave, right here. But this AC out now contains a lot more current than what we use for a trigger. So what essentially happens here is you get a dual action. You get the displacement current from modulating, and then you also get the quasi-state, semi-quasi-state DC bias being modulated. So you're embedding this current into the field and modulating it. So because it's a pulsing action, the transformer automatically gives you back a sine wave on the other side, you see? And that's why the filtering is very important, and you get your AC 110 volts out at high current. So I'm just going to make it up, but let's say, you know, with our values and everything, we end up with 110 volts, 1 kilowatt instead. on our load here due to this action, because essentially what we're doing is we're stacking the displacement current of the high voltage and modulating the current and embedding it into this mostly static DC field. So what we're doing essentially is breaking the linear VI response of a typical transformer action and taking advantage of displacement current and the carrier wave of the semi-quasi-DC state. This is basically a form of bias, but you can modulate it and extract power from it. So essentially, I think this is what Don Smith was up to at the core. This is really easy, but probably in the reality, you might only, I think this might be limited. You see, so let's say we get like 200 watts out. Now, Don Smith seemed like he was all about commercial quality power, where he wanted to essentially build a power plant version of this. So that's where he got into extended prototypes, where he figured out with the addition of more complex interaction, like with ion valves and higher voltages and ground loops, that once this thing was started, he could eliminate the trigger power here, and the device would keep essentially the high potential going without feeding into it through the various interactions. So I get his idea for wanting to save on the input power requirements here, but keeping things simple, it's really not that much money for me to have to provide it if I don't have those ground loops and ion valves and all the complex. Now, of course, again, Don Smith wanted to build a commercial prototype, basically a power plant version of this. So he was somewhat deceptive about it all, and potentially didn't want to show you the more simplified version, which could run basically everyday home loads, because he was after for the power plant. I guess he wanted big money. Maybe the sun had a delusion vision. I don't know what it was, but everything essentially that came out of Don Smith's mouth was almost a deception. So at the end of the day, he was showing, really high-tech capacitors, which at the time he figured making better dielectrics and such things, which were, essentially side projects, not completely relevant to the core action going on. Essentially, it's like he was using the lava lamps as a distraction from the main thing, is what I'm getting at. Good information, but, sure, if you want to learn about resonance and fields and that sort of thing, but really hardly directly applicable to this. So I just wanted to clarify that yes, you can go really complex, but the theory here can be quite simple as well. So by the way, the reason I wanted to split the core here is so you don't interfere with the trigger, but that's just dumb me way of doing it. Maybe someone can figure out an even more efficient. But just to quickly demonstrate here what goes on, this is what goes on. So I hope, again, I've clarified a few things, and again, how we can break the linear interaction of typical transformer if we basically run the whole thing backwards. So with that said, folks, always looking forward to your comments, and have yourselves a great day.